Good. Okay. Recently, I'm reading the paper about the non-perturbative effect in jetty gravity. Actually, we know that the jetty gravity and the jetty supergravity is due to a matrix integral. So, you know that any correlation function in the matrix ensemble can be altered by some topological recursion relation. That's easy. You can calculate it. But this paper shows that there is another way to solve this the same mathematical equation. That is to use the orthogonal polynomials to study the double scale limit of the matrix ensemble, which means that we take the dimension of the matrix n to go to infinity, while we are just we can just consider about the behavior of the eigenvalue distribution near the edge. Okay, this is what we want to discuss. And the how to say? I found that this paper contains most details in the derivation. Okay. In fact, I think it's just a mathematical technique. It's not about physics, I think. Okay, but it's in some sense it is also interesting. I think it's because that the author shows that the non-perturbative or the compact density of the jetty gravity can be written as a sum over some quantum systems distribution of its eigenvalues. I think so. Maybe that's a little interesting. Okay, let's begin. This is the motivation and all the story and the total story. But we need to do some calculation. Then I seek for more papers. I want to know if anyone use the same method to study the jetty gravity with defect. Anyway, you can use this method to study any matrix integral with any potential. So in principle, you can do everything. But I don't know if we can use the same thing to calculate the two matrix model. You know that when we couple the jetty gravity to some matter, that's because, for example, we have a phi, a scalar matter in the bulk. Okay, then in boundary, on the boundary, it should it will become an operator. We denote is O. Okay, and the plus Hamiltonian, we have two random matrix. It is a two random matrix model. Maybe we can use the same way to discuss it. But I found it's impossible for in some sense, because when we in this paper, he just write the determinant, the Jacobi determinant in terms of the orthogonal polynomials, and in this process he must to have some weight. Yes, in the weight that any eigenvalues and the contribution of any eigenvalue should be factorized. This is a key point. But for the two matrix model, I think it's quite difficult to do it. Actually, you can just integrate one matrix. So you will need a very complex matrix model. It should be a Gaussian matrix model, but the operator you insert can be quite complex. It is not a polynomial, but a fraction function. It means that the eigenvalue will appear in the denominator. You dislike it. You don't know how to expand the fraction function in terms of the polynomials. In principle, it's impossible, I think. But maybe you can do some approximation by saying that the Q tilde is quite small, so you can do the Taylor experiment. But I don't know how to do it anyway. Then I need to do some calculation. Okay, first I just write down all the derivation in my notebook. So now I need to record. Okay, first one. Yes. We know that the jet gravity is due to a matrix integral with the leading density, which is unknown. So let's consider the matrix model. Okay, whose measure is denoted as the tilde. It should be the, okay, I make some mistake. No, lambda I. This is the determinant. This is the beta equal to beta 2 that's in symbol, and this factor is potential. Okay. You know that you need to notice that this thing, due to the summation, appear in the index of the exponent. So it actually can be written as a product of any of each eigenvalue. So it is a key point to use the orthogonal polynomials method. Okay, that's great. Actually, in jet gravity, we want to calculate this trace. We take the jet gravity average. It should be equal to the random matrix average. Okay, that's great. But actually, we don't need to. We want to calculate it. If we can find a basis or a series of the orthogonal polynomials, then we can calculate any correlation functions in principle. That is because here when we see any correlation function, it means that those operators can write in as a linear combination of these orthogonal polynomials. So as I mentioned before, if you have something where the lambda appear in the denominator, then it is hard to deal with it, I think. Okay, anyway. And then if we can find some orthogonal polynomials for h lambda, that is as d lambda, pn lambda, pm lambda. Maybe I can use, okay, just use this color. And the weight is minus mv lambda. Okay, you notice that this thing is factorized. Okay, that's great. It should be equal to delta nm hn. That's great. Okay, good. If we can find this, then you can, in principle, you can write this. Okay, actually it is a general polynomials. Then you can, in turn, you can write it as ck, pk, lambda 1 or any pk2, lambda 2, and anything. Okay. So it's quite easy to calculate. Okay. Now the key point is to find the expression of the Pn actually. Yes. Okay. Then what can I do? What can we do? Then you can. Then there is a recursion relation. Here the index m is used to denote the order of the polynomials. So we may have a recursion relation, and is lambda times Pn equal to Pn plus 1. You notice that there is a normal factor, so you can choose the factor Hn to make the coefficient appear here to be 1. So the next is Rn Pn minus 1. Okay. I don't know if such a recursion relation appears for any weights and any potential, but for Gaussian mode, sorry, for the Gaussian model, or anyway, for this thing, we can always find such orthogonal polynomials. Okay, good, great. Then what can I do? In principle, we can here we just assume that the potential with lambda you choose the is choosing even, so that you can easily find this integral should be. You should notice that here the lambda takes value from minus infinity to plus infinity to positive infinity, so you will easy to find this that this is n should equal to 0. That's because this thing is just it's an odd function, and this thing is an even function. So the whole integral must be 0. Okay, great. Then what can I get for this equation? No, I don't. We can do nothing. We need another constraint or another condition. And my personal idea, I think it's another. I don't know how to prove it. That is Pn minus 1 lambda d lambda p. Yes. In principle, you know that because the order of Pn is n, and we apply derivative over lambda on it, so the total the total order of this thing is just minus 1. So the integral must be proportional to minus 1. We can choose the proportion coefficient to be n. Okay, this is a key point. Okay, we can choose it. Anyway, we can choose it to be n. Then use this equation and the recursion relation. We can derive the relation of Rn. Actually, if we know Rn, it's quite direct to calculate the orthogonal polynomials. You can start with P0 to P0 to be a constant. So anyway, you can calculate it. So it's enough to just calculate Rn, and we can solve the problem. So now the key point here is to derive a relation for Rn. How do it? Maybe what can I do? What happened? Let me also forget it. So okay, we need to consider. What do we? Let me see. We consider to do an IBP, which means integration by parts. Then the left-hand side should become to this one, lambda partial lambda d to n with lambda Pn minus 1 lambda, okay, times p and lambda. Okay, that's great. You need to notice that the v the potential go to infinity for x go to positive and minus infinity. So the boundary contribution vanish. So we get this thing, and we can get this operator act on the first turn and the second turn. We get something. Let me see. When we act on the first turn, we have that is m sum over minus v lambda v prime lambda p n minus 1 lambda p n. When he act on this one, sorry, here we choose what? We choose what? We choose p minus 1. Let's see. Oh, let me see what I make. If I make some mistake. No, I don't make some mistake. It is p. It is pn, not p minus 1. So this is pn. Okay. This one. Let me see. What is another term? Another term should be that it is partial lambda act on p minus 1 times pn. Okay. This term should vanish. Nothing because the order of this term, this part is just n minus 2. So its contribution on the Pn is 0. So this part go to 0. It should vanish. So finally we get this. This should equal to n minus 1. That's great. Then okay, we know that the potential is taken as polynomials of lambda. So its derivative should be the polynomial of lambda. Then you can use the recursion relation to write this a linear combination of the orthogonal polynomials. That is pk, state k. You just have to take c minus 1. It should be 10. Okay. The left hand should be equal to this. Then you can cancel you can cancel hn on both sides. So you got this equation. Then c minus 1 should be a function of Rn, or then you can got some recursion relation for the Rn. That's great. It's quite easy to do it. We'll take something as an example. For example, we consider the simplest one, that is Gaussian mode. So model. Gaussian model. The wave prime lambda equal to lambda. So we have the equation lambda a minus m v lambda. It is pe and lambda. We can write this one. Anyway, it doesn't matter. It should be n actually minus 1. Okay, so sorry. We should use this part times v prime times pn and write it and decomposition it and decouple it. Okay. Anyway, we need to write this thing. What can I do? From the recursion relation, we know it equal to it equals to what happened? P n plus 1 x plus Rn p minus 1. So only this part contributes. So we finally get n Rn equal to the hn minus 1 cancel. So we know that Rn equal to n over a character n. Okay, that's great. It's quite easy. You can do the same thing for lambda equal to lambda square plus g4, sorry, and 4. I cannot use Chinese. That's great. It's easy to calculate it. You can find that. Okay, I need to write it. The v prime should be 2 lambda plus 4 times d4 and 3 and 3. Then we need to calculate. Actually, we need to project this into Pn minus 1. This is what we want to do. This thing have been calculated is just to n. Okay, that's great. We just need to calculate this. Finally, we have found that it is 4g4 n plus n minus 1 plus n 1. Okay, this is the final result. There is n here. Yes, this is overall factor. So finally, we got n plus 4 n plus n minus 1 plus n plus 1 equal to n over the factor n. Okay, that's great. Okay, great. And one can see that hn equal to hn plus 1 over n plus 1. How to do it? You can have try to find it. Maybe we can just denote. We can just to denote p n lambda. As a wave function. Yes. Then we know then the recursion relation can be written as the lambda times the nth polynomial equal to the n plus 1's polynomial plus n times n minus 1. Okay, this one. And you have the two conditions. We consider, we know that lambda dagger is equal to lambda. Yes. So we consider this. We can say that to use a Microstate act on the left. So we have n plus 1 lambda n equal to hn plus 1. Okay, that's great. But as operator lambda can act on the left, the left side state. So we got this one. Okay. And you found that the left hand side should be equal to r plus 1 hn and equal to hn plus 1. So this is the result we want to take. Okay. Let's move to the calculation. Let's calculate the tilde. So the principle, the task is just to write the determined as the random mode determined to write it in terms of the orthogonal polynomials. It's quite easy. It's b j minus 1 and I n I j from 1 to n. Okay, that's great. And then you find that the detailed calculation will give that this effect, this result equal to 0 n minus 1 h n. Finally, we will get h0 n exp n squared times 1 over n sum over and from 1 to n minus 1. Why is minus 1? Let's see. Okay, anyway, yeah, that matter. That is log. Okay, great. The revision is quite direct, so then we can take the continuous limit, which means that we just denote x equal to n over larger. It should belong to 0 to 1. Then we just take this one. Okay, we just to take the free energy to integral from 0 to 1 x 1 minus x on here. Yeah, log on x. Okay. And then our target is to calculate Rx. If you want to insert some operator O here, you need to what can I do? You need to expand the operator O times the random mode determinant to write it in terms of the orthogonal polynomials. Then you can go to the final result. It seems not easy to calculate it for a general O. Maybe so I don't know how to do it. Maybe you can develop some IBP relation to calculate the correlation function recursive, but I don't think it's a good method. Okay, great. Okay, great. Then what do we want to do? Okay, we need to recall that we need to know that the total task is just to calculate Rn, and we have obtained some recursion relation about Rn. For example, for the quadratic case, we have the relation to Rn plus this one, n plus n minus 1 plus n plus 1 equal to n plus 0. And if we denote Rn as Rx, and we denote epsilon is 1 over n, for n is large, epsilon is an infinitesimal parameter. So this one should become Rx minus epsilon, and this one is Rx plus epsilon. Epsilon is quite small, so we can do the Taylor expansion. And we will finally to take n go to infinity, but now we will keep n as a large number. So you will have an expansion about 1 over n of Rx. It should become like this: Rx k 1 over n. Okay, great. For the leading order, there is no difference between Rx and Rx minus epsilon. So these two things are just equal to each other. So it's easy to solve this equation. You get then the final result is Rx equal to, let me see, it's 2a. You need to calculate it. What is A? You just replace this 3 x, so it's this one. Okay, great. And it's -2, and it is this is b squared. What is b? This is b squared. 4 minus 4 times a. What is a? A is 12 t4. What is c? This is c. C is x. Okay, c is minus x, so it's plus x. Okay, great. Then you can simplify it to 12 t4 minus 1 plus or minus 1 plus 12 t4. Okay, that's great. Oh no, there is an x here. Great, very nice. Recall that for the simplest case, the Gaussian model, Rx equal to x. Okay, that's great. Then we notice that there is a critical value. What is the critical value? That means to make the square to vanish. That is, so we can take g. Sorry, this is not critical value. For this part, for the simplest solution, we found that Rx equal to 1 will get to 1. This is quite easy to think it. Let me see. There's no x, sorry. Why? Why there is an x? Let's take just equal to 1. It's amazing that if we take g4, go to 1 minus 1 over 12, and we will find that this r x equal to 1 will go to equal to 1. So we see that this value to be critical. This is yes, because it gives us the r takes the value 1 at the edge of x. Then what can I get? What can I get? Nothing. In this paper, we will always discuss the critical case, and maybe it should be due to the minimal string, I think, but I don't know. I know nothing about the string, so I will not discuss it. Okay. What is the key point? The key point is that you may imagine that you want to calculate the density distribution. So you need to calculate the ensemble average of the trace A to beta H. So you will be worried about how to write the exponent to the exponent operator times the determinant to write in terms of the orthogonal polynomials. You may worry about how to do it. Actually, don't need to solve. Someone have derived it. They found that the density, though. Oh, let me just discuss the needing order. The needing order it must be related to R, but we have a simple equation. This one, lambda square. Okay, good. It's R. Once you have gotten the needing order of R, okay, that's great. maybe you can compare with its solution around matrix. Q is an analytic function of lambda. This is branch cut. Okay. So the leading distribution of lambda should look like this figure from minus a to plus a. Okay, it's great. It's symmetric. Okay, we just accept it as a conclusion. Or you in principle you can just do derivative by the use the orthogonal polynomials. But the trouble thing you will meet is that the operator you insert is an exponent. It is not a polynomial about lambda. Maybe you need to do the Taylor expansion about the beta. So it's troublesome. It's troublesome to do so. Here, I just think of that. Why don't we consider other orthogonal functions except polynomials? We can choose some. I think actually what we do is just to choose a basis, a function basis. When we choose a function basis, it is actually equivalent to the one-dimensional quantum mechanics. Yes, and lambda is real. So, so you know that for the Gaussian model, the orthogonal polynomials plus its potential factor, it is just the wave function of the orthogonal of the harmonic oscillator. So actually, all the things is just quantum mechanics, I think. Yes, but you can. But this thing. Oh, that's great. This thing is factorized. That's because we just take a trace. So it's just like this one. Okay. So you can just observe this term as a linear term in the potential. So then, but it will give some trouble. So that's because in the derivation we have assumed that the potential to be an even function. Yes, to be an even function. But now if you just want to interpret the operator as one part of the potential, then the potential can have the odd part. So you need to reduce all formulas before. This is what I want to comment. Yes. But if you want to calculate other thing, that is, if you want to calculate the spectral form factor, so you will meet something like lambda, beta 1, right? Beta 2, lambda j, small I, small j. What can we do? That's great. And also, can we to calculate it? It just gives that. Let me see. It's just equal to beta 1 plus beta 2 times lambda I. So it's quite easy to calculate it, I think. But in this paper, it shows that once we have obtained the expression of R, we make a double scale limit. Then we we found an equivalent description of this system, that is, it is a quantum mechanics system. Then you can solve it to get the wave function. Have the wave function in hand, you can calculate anything you want. Then you can calculate the spectrum form factor. So I'm a little puzzled about why he can calculate the spectrum form factor using a elegant formula. I don't know why. In principle, you need to interpret all these insert operator as polynomials. It's not easy to do so, I think. Where? No, this one, not this one. Here. I don't know why. Okay, maybe it will use in the future. Okay, that's all. I think in the next time I will discuss the double scale limit. Okay, great. That's then.